The contribution of ICT devices energy consumption has been estimated as around the 2% of the worldwide carbon footprint in 2007, and it's expected to quickly grow by 2020. Such huge amount of energy consumption leads to environmental concerns and implies high costs for operators and customers. Furthermore, the energy starvation of ICT devices also brings technical issues related to the management of ICT infrastructures. The current trend is no more sustainable, and the need for energy-aware ICT systems is widely recognized. Estimations and forecasts point out that a large share of energy consumption is due to telecom network equipment and personal computers. Moreover, such infrastructures and devices are usually very inefficient, in that they often consume about the same power independently from their actual workload. In such a scenario, the EcoNet project is addressing the optimization of the ICT devices' power consumption by fully exploiting and enhancing their performance, adaptation, and low power state capabilities. In the following, I am introducing the concept of Network Connectivity Proxy, or NCP for short, which allows to make a more efficient use of the standby states already available in most computers and in many ICT devices. The design, implementation and standardization of the NCP are jointly addressed by the Italian National Inter-University Consortium for Telecommunication, by Infocom, an Italian SME, and by Telecom Italia with the support of the German Lantic. Today's networked devices are often left powered on, even if nobody is using them. There are several reasons behind this behavior: to allow remote access, the need for system administrators to access PCs at night time for maintenance operations, running background applications as, for instance, voice-over IP clients and peer-to-peer applications, and finally, even users' wrong beliefs. For example, some people think that screensavers save energy, others do not know about the power modes and do not know how to access their configurations. Keeping computers powered on all the time implies a large energy waste. Studies by the Lawrence Berkeley National Laboratory revealed that about 60% of the office computers are left powered up 24/7 with the existing power management features disabled. Only 36% of them are turned off when unused, and only 4% of them have the power management features enabled. This means that most of the energy is simply used to make the devices present and available, and not for their actual use. This implies a large energy waste. As a matter of fact, a typical last generation PC can save, on average, up to 60 watts by shifting from idle to sleep. This would lead to a save of 400 kWh per year if it were put in sleep mode for 75% of the time. So, the question is, how can we allow the usage of low power states without breaking devices' network connectivity and availability? The Network Connection Proxy is a low power network entity that acts on behalf of other devices. The NCP maintains the network connectivity for the sleeping networked devices and wakes them up when needed. This way, the covered devices looks always on and available to their peers. Now, let's take a quick look at what the NCP concept involves.
Consider the scenario of a local area network where a computer is idle and is put in the standby mode by its power management software. The most common sleep mode for quick availability is the so-called suspend to RAM. All device hardware is powered off, but the memory and the network interface card. In this state, the device cannot answer ARP or ICMP requests. It cannot take part into protocols like NetBIOS, Bonjour, UPnP, and it cannot refresh soft state by keep alive or earth-beating messages. This usually turns into unreachability errors for any host trying to access the sleeping device. Indeed, the sleeping host network interface card remains powered, and it can wake up the host on the reception of wake on LAN packets. However, this would require any host to be aware the peer is present and sleeping, and to send the wake on LAN message. Instead, if an NCP is present, it intercepts the traffic addressed to the sleeping device and answers on its behalf. This way, the NCP hides the current power state of the covered devices.
Maintaining a host network presence mainly implies preserving host reachability, host manageability, and application reachability and state. In other words, and to sum up, network presence essentially includes three main issues: link layer presence, namely maintaining physical connectivity; network layer presence, which means an active participation in networking protocols to maintain end-to-end reachability; and application layer presence, which includes all the messages and the functions to let other peers believe that specific applications are active and ready to answer. Packets addressed to sleeping host can be classified according to the treatment they need. There are different options. First, no response is required, when the packets can be discarded or ignored. Second, a minimal response is required, when the answer is really predictable and no heavy computation is needed. Third, delay response required, when the packets can be buffered and processed later without affecting the remote application. And finally, wake up required, when the involvement of the sleeping host is mandatory. To properly handle these kinds of messages, the NCP has to perform four basic types of function. First, responding to routine requests, as for instance ARP and ICMP protocols. Second, automatically generate routine protocol messages, as keep alive or earth-beating messages. Third, waking up the host when its functions or resources are strictly necessary. So, for instance, when there is an attempt to access data stored on the disk or application that is running on the host. And finally, ignoring all the other messages.
The communication interface between the NCP and the covered devices should support mutual discovery, event notification, and remote procedure call and registration. The client devices should instruct the NCP about the network services they need while they are sleeping, and then should notify the NCP when they are going to sleep. The NCP operates on their behalf until their wake up. UPnP, web services and SOAP are all technologies suitable for the implementation of such communication infrastructure. Another interesting matter is the location of the NCP service. One simple and scalable solution is to place the NCP on board of network interface cards. Modern network interface cards have increasing processing and storage capability. Furthermore, they consume very low power and are expected to be always on for the wake on LAN feature. Indeed, some network cards already include simple NCP capabilities, as for instance answering ARP requests and waking up the host on incoming traffic. However, the filtering and processing operation cannot become too complex, otherwise too much computational power and energy would be required to serve a single host, and so reducing the achievable saving. Another option is putting the NCP on network equipment as hubs, switches, routers and home gateways. Many of these devices are often equipped with hardware accelerators for packet filtering and classification, and this greatly simplifies the most resource-starving task of the NCP. The NCP service could also be deployed on a standalone device. From the perspective of energy balance, this is the most critical solution, as the standalone device must consume far less power than the one saved by putting in sleeping mode the covered devices. However, high memory and high computational power would be available, and this allows the implementation of complex routines for a large number of applications and hosts.
The NCP topic has already raised interest within standardization bodies and in the industry. Support for low-power devices and proxies are envisioned by the UPnP low-power architecture. Apple ships Bonjour Sleep Proxy with its latest network devices and Mac OS. This solution provides a transparent and zero configuration way to wake up hosts when applications using the Bonjour protocol need to be accessed. Microsoft's Windows 7 supports enhanced power management features, including the capability to configure in the network card incoming traffic patterns that trigger the host wake-up. Finally, commercial NICs are starting to include packet classification, patterns matching and TCP offload capability that allow network cards to answer packets and selectively wake up the host. The work that we are going to show in this demo is the result of our effort towards a very general and flexible design of the Network Connection Proxy. We conceived a quite complete set of NCP actions to support the operation from low-level networking tasks up to TCP and application-level keep alive and heart beating. We also devised a rich UPnP interface for the interaction between the client devices and the NCP module. Currently, we are promoting this interface within the Home Gateway initiative. Our design covers different applicative scenarios where the NCP service can run alternatively on the host's NIC or on networking equipment or on standalone devices, so with no constraint about the deployment of the NCP itself and about the network topology. Our current implementation targets a local network, but we are working to extend the NCP to the Internet so that it can be supported in cluster or data center and can be provided to thousands of users.
Our demo of the NCP capabilities covers a typical home scenario that includes devices as a set-top box, a XDSL modem or home gateway, laptops and desktops. In our demo, the NCP is supported on the home gateway device. We will show how the set-top box discovers the presence of the NCP and how it registers the request to be woken up when the user requires to access a video. Then we will put the set-top box into the sleep mode and we will demonstrate that it will be anyway seen as up and running by a client, as the NCP will answer the ping messages on its behalf. Finally, we will show how the set-top box is woken up and becomes ready for service when a user simply requests a video.
Set-top boxes are interesting devices for what concerns power consumption. They have standby states, but they need to be quickly available in the network either to provide services or for firmware and configuration updates. As a result, they do not actually exploit their standby capabilities. So, providing NCP service to set-top box devices does make sense.
Our demo includes the minimal set of devices that are suitable to demonstrate the NCP function. First, we have the set-top box, which is emulated by a small PC with similar power requirements. A power meter measures the set-top box power consumption to evidence the actual device power state during the demo. Then we have a laptop, which the user will use to watch a film stored in the set-top box. And we also have a development board which implements an ADSL gateway where the NCP service will run. All these devices are connected via a simple switch. Let's see now how the NCP works. When the NCP started, the UPnP interface advertises the service on the network. Once the NCP client sees the advertisement, it knows an NCP is present and can register with it. Then the set-top box registers the requested actions, including the support of ICMP on its behalf and the wake-up conditions. Now the set-top box is unused, so it can enter the standby mode. As we can see, the power consumption drops from 23 to 6 watts. Once the user sees at the laptop, the set-top box is still sleeping, but the NCP hides this condition. Indeed, if the user tries to ping the set-top box, she'll get an answer as the device were up and running. The green window is showing the NCP activity log. Finally, the user requests a video from the set-top box. The NCP detects the connection request and wakes up the device. The power meter shows the device is back to the active state. And the user can now enjoy her video.
We developed a general software framework to provide a set of different services to multiple networked devices, and the NCP is just one of them. As far as the NCP module is concerned, it can be considered made by three basic building blocks: packet filtering, packet processing, and rules. Packet filtering is used to classify packets and recognize those that need a specific treatment. Packet filtering considers packet headers for several layers of the protocol stack and can do pattern matching. Packet processing carries out specific operations in response to packets intended to sleeping devices. It can answer packets, can generate new packets, can wake up the hosts. The packet filtering and packet processing blocks act in accordance to specific rules which encode the behavior requested by the client to the NCP. The NCP is provided with the communication interface towards the networked devices to allow their discovery, to register and modify their associated rules, and to exchange power state information. The NCP starts processing a specific rule when the associated device enters the sleeping state and stops when it wakes up. As already stated, we are currently using the UPnP, so the Universal Plug-and-Play Protocol, to implement the communication interface between the NCP and the clients. We have defined a specific service model for the NCP, and we have used the UPnP low-power architecture to allow the NCP to monitor and control the power state of the networked devices. Let's now see what the NCP can really do. Our NCP can currently answer ARP requests, it can answer ICMP equal requests, it can send periodic DHCP renewals, and it can wake up and host in case of a new TCP connection request. The design also includes the host wake up on specific packet arrival and the reply to a packet with a predefined packet. Now we are working to extend this behavior to support more challenging functionality. In particular, our goal is to keep TCP connection alive and to provide the support of generic applicative heartbeats. Finally, some ideas about the future developments. Our target is to bring the NCP beyond the LAN boundary and to move it into the Internet. Indeed, this requires to rethink many of the NCP mechanisms. As a matter of fact, putting the NCP in the Internet implies to face new issues related to the host NCP communication, to the traffic diversion mechanism, as well as to face the additional complexity due to network mechanisms as NAT and firewalls.
Nevertheless, moving the NCP service in the Internet opens new opportunities. The NCP service could serve thousands of devices, and the energy saving might be so high to allow to deploy the NCP on high-end hardware. This way, more advanced features that requires high processing capability could be supported. If we deploy two instances of the NCP service, one in the home network and the other one in the ISP network, we can obtain energy saving in the access network. In this scenario, a client device discovers the local NCP instance and registers its rules. The local NCP offloads these rules, at least the part that are relevant to the external traffic, to the Internet NCP. Then, when the device is sleeping, the two NCP instances manage the traffic addressed to covered hosts in the home and in the Internet independently, and in this case there is no need to forward traffic on the access link until the device must be woken up.
The Network Connection Proxy can be a powerful solution to increase the energy saving by fostering the network host's standby capabilities. Furthermore, when provided within the Internet, the NCP also benefits the access network power consumption. If you are interested in more information and wish to collaborate with us, please visit the project website. Thank you for your attention. Bye.